Hello guys, welcome back. 8.3, we're looking at trig substitution. So the main point in this section is we want to rewrite some expression as a trig function. Okay, so let's start with a quick example. Let's say I have square root of a square minus x squared. Okay, so let's look at a triangle together. Alright, so we have this right triangle, and now we have the angle alpha right here, and the hypotenuse, let's say, has length a, and one of the leg has the length x. Okay. All right. Then by Pythagorean theorem, we know that the other leg is going to be a square minus x squared. Okay, so this one of the leg happens to be what we're looking at in this right triangle. So we're gonna play around with this and see what we can do with it. So first, let's let x be equal to, actually no, we're going to look at sine theta first. Sine theta is going to be opposite over hypotenuse. Right? So x over a. Then what this is saying is I can write x as a times sine theta. Okay. All right. Then let's go back and look at our expression. Square root of a square minus x squared. Then we can rewrite that as a square minus quantity a times sine theta squared, right? Which will give us a squared minus a square minus sine theta squared. Right? And then we can simplify it by factoring out a squared times 1 minus sine theta squared, which is equal to the absolute value of a cosine theta. Okay, so if you look at the triangle here and then figure out what cosine is instead of looking at sine, right? So cosine theta is going to be square root of a squared minus x squared over a. Then that will give me square root of a squared minus x squared is a times cosine theta. Right. Now we have the absolute value here because we're not sure if cosine is going to be, in this case it's going to be positive because it's an acute angle. Right. So since a is always positive because we're talking about distance, and cosine theta is greater than or equal to 0 for the domain negative pi over 2 to pi over 2. We can drop the absolute value sign from here and just understand it as this expression that we have here. Right? So square root of a squared minus x squared is equal to a cosine. Now this is going to come in handy when we have to perform integrals in the next section, and we run into something like this, right? Then we will do something called the trig substitution. Right, so now let's look at some of the others. Part 2, we have square root of a squared plus x squared, or x squared plus a squared. So you will notice that the difference between the first one and the second one is now here we, instead of minus, we have plus, and since addition is commutative, we have both of them. Right? And the idea is still the same. It comes from a right triangle. All right, so same thing. Let's say we have theta here, In this case, this triangle is going to look a little different. We're going to have the legs being A and X. That way, when we look for the hypotenuse, we get square root of A square plus X square. Okay. Now, in this case, we can write start by finding tangent theta. Tangent theta is going to be opposite over adjacent, right? So X over A. Okay? And then you perform the same technique, letting X be equal to A times tangent theta. And then plug this X back in here, and then we will get that square root of A squared plus X squared is equal to A secant theta. All right, so our goal is to represent, to find the ratio that has the expression we want and A. Right? So in this case, we have adjacent and hypotenuse. Right? So want adjacent and hypotenuse. Right? And the ratio that gives us adjacent and hypotenuse is cosine. Right? So let's see. Cosine theta is A over radical A squared plus X squared. Right? But if we do that, we multiply the denominator over, right? And then maybe divide the cosine. We get square root of A squared plus X squared is A over cosine theta. Now we know if cosine theta appears in the denominator, we can rewrite it as A squared plus X squared as A times secant theta. Right? And that's how we get this expression, right? We can rewrite square root of A squared plus X squared as A times secant theta. Now notice that we have no idea what theta is or X is, but we're just doing an introduction on Trig sub, and then later on we'll see how we can put into work. All right, the third part, we have X square root of X squared minus A squared. Right, so same idea. We're gonna have a right triangle here somehow, but for this one, I'm going to do it a little differently. I'm going to start by let X be equal to A secant theta, right? So that's going to be from a triangle as well, and the triangle will look like something like this. So theta here, X here, A here, and square root of X squared minus A squared. Okay. All right. So secant would be hypotenuse over adjacent. All right, and then we can keep going with the calculation. All right, so X squared minus A squared is now A squared secant, secant squared minus A squared, which gives us A squared parentheses secant squared theta minus 1. And secant squared theta minus 1 would just be a tangent square. Right, so we get A squared times tangent square, which is absolute value of A tangent theta. All right, so now we want to be a little careful. We cannot just drop the absolute value like the previous two, because tangent can be negative in some for some x value. All right, so to sum it up, x squared minus A squared is going to be A tangent theta for x greater than A. Right? If x is greater than A, then x squared minus A squared will be positive. Right? But it's going to be the opposite. Use a different color here. It's going to be negative A tangent square a tangent, tangent square, a tangent for x less than or equal to a. Okay, because we have to consider when theta is between pi over 2 and pi. Sorry, a little mistake. It should be less than negative a, right? So absolute value wise, x is still greater than a, so we can still define this radical will still be defined. It's just that when x is less than negative a, we will have a negative value from a tangent theta. Therefore, we need to add an extra negative sign to make it positive. So that's equal to this radical over here. So what I'm saying is, get the colors change. So this thing here will be negative, right? If x is less than negative a, and we need that extra negative sign here to make it positive. All right, so here we have a quick summary of all the three trig sub that we talked about, right? And as well as how to find them. So square root of a minus x squared, that will be a cosine, and square root of a squared plus x squared, that will be a secant, and x squared minus a squared will be a tangent or negative a tangent, depending on your x value. Okay, so let's talk a little bit about what we're going to do using these three things. And let's look at some examples. All right, so example 1, we're looking at a definite integral from 1 to rad 2 of dx over x squared minus x squared times radical 4 minus x squared. All right, so the first thing that we want to identify is what type of trig function we need to use. Or another way to ask this is, when do we know we want to use a trig function, or trig sub? Right, so we look at this radical right here. It doesn't look like any u sub or any directly inverse trig integral. Right, so let's look at what this looks like. So 4 minus x squared, we can understand this as 2 squared minus x squared. All right, so we want to find out what form this looks like, 1, 2, or 3. So let's go back a little bit. Right, so 4 minus x squared, that looks like a squared minus x squared, right? It's not a squared plus x or x squared minus a squared. So it's a squared minus x squared, which is the first case. So the first case, we know that we have to use let x be equal to a sine theta, right? And what is a and x in this case, right? We're not sure. So let's come back here, right? In this case, we know that a is 2, right? Right here from the 4 here. All right, so first we're gonna let x be equal to 2 sine theta. Okay, and let's rewrite this whole thing and work it in terms of theta. Right. Next, let's take the derivative of x equal to 2 sine theta on both sides. Where you get dx is 2 cosine theta d theta. Okay, and that takes care of this part, right? We know what 4 minus x squared is going to be, square root of 4 minus x squared, and we also need to take care of the x squared, right? In this case, x squared is going to be very simple. You just take whatever x is square, so x squared is going to be 4 sine theta squared. Okay, so let's rewrite this integral a little bit. So we have integral from 1 to rad 2, right? And then we have dx in the numerator, dx, x squared, which we found as well from here, and then square root of 4 minus x. Right. All right, and let's rewrite everything in terms of theta. So actually, before we do that, there are two ways to approach this integral. The first way is by doing the limit switching. Limit switch. Right? Meaning we're going to rewrite the limit from x to theta. So let's look at this. So the upper bound, x equal to rad2, means rad2 is equal to 2 times sine theta. Right? Then sine theta is rad2 over 2. Right? So what I'm using here is this first trig sub, right? X is equal to 2 sine theta. All right, so sine theta is equal to rad2 over 2. That means theta is pi over 4. Right? And the lower bound, x is equal to 1. We get 1 is same thing, 2 sine theta. Then sine theta is 1/2. That means theta is pi over 6. All right, so our new bounds for theta will be from pi over 6 to pi over 4. Right? And let's rewrite that. All right, so pi over 6 to pi over 4. And we're going to rewrite everything in here using our trig sub. So dx is 2 cosine theta d theta. X squared, that's 4 sine theta. And what's square root of 4 minus x squared? So let's go up a little bit and look at our first one. So we know that if we started by using x equal to a sine theta, then square root of a squared minus x squared will be a cosine theta. So in this case, radical 4 minus x squared will be 2 cosine theta. Now, it's okay if you forgot, but if you picked the right trig sub, let x be equal to a sine theta, we can always derive that from this radical. So let me show you real fast. So we have 4 minus x squared, which is 4 minus x is 2 sine theta, so that will be 4 sine theta squared, which will be 4 times 1 minus sine squared. And we know 1 minus sine squared is cosine, so that would just be 2 cosine theta. Okay, so times 2 cosine theta. All right, so we're going to see that the 2 cosine theta, they're going to simplify each other out. And then you're left with the 1/4. I'm going to put it on the outside. Pi over 6, pi over 4. And now we have 1 over sine squared, which is cosecant square theta. Now, integral of cosecant square is just negative cotangent theta, right? And we want to evaluate that from pi over 6 to pi over 4, which will be 1/4, and then cotangent of pi over 4 is 1, right? So negative 1 minus, and the cotangent of pi over 6, that's so we have the negative sign, so negative rad 3 over 2 divided by 1/2, which will be 1/4 times, that's positive rad 3, so rad 3 minus 1. Okay, so that's how we use a trig. This is one method, limit switching, and the other one, in my opinion, is the easier one, which is just using the triangle. Well, maybe not that easy, but it also makes sense. It depends on your personal preference on what to use. All right, so let's look at the triangle approach. So using, all right, so the other method, using the triangle, we're going to do similar thing, but this time around, we're not going to touch the bounds, right? So we're gonna still have the same integral, right? After we do the u sub. All right, 2 cosine theta d theta for sine squared theta, 2 cosine theta. Right, and then we're going to cross everything out. Well, not everything. And then we're left with 1/4 cosecant square theta d theta, which is negative 1/4 times cotangent theta. Right. So one more step from here. So in the previous method, we just used evaluate the bounds from pi over 6 to pi over 4 here. But what we're going to do here is we're going to rewrite using x. Right. So how do we go back to x? Right. And here is what we need for the triangle. Right. So the triangle that we're going to use is from the first one that looks like this. Right. We have the angle, opposite is x, a on the hypotenuse. All right. So here we go. Let's say theta is here. Right, opposite is x. Hypotenuse is a, which is 2 in this case. Then the adjacent will be 4 minus x squared. All right, so we have cotangent theta. That means we want to find out what cotangent is. So cotangent, tangent is opposite over adjacent, right? So cotangent theta will be adjacent over opposite, which is adjacent. That's radical x squared. Oh, oops. 4 minus x squared over x. All right, so cotangent is going to be that, and we can just replace that. Replace cotangent with radical 4 minus x squared over x. And then evaluate it from the same bound, which is 1 to radical 2. And we evaluate that, so we get negative 1/4. The first one is going to be radical 4 minus 2 over rad 2. Minus radical 4 minus 1 over 1. And let's see what we have. That's negative 1/4. That'll be rad 2 over 2, so that's just 1. Minus, that'll be rad 3. Okay, now it's actually the same as the previous one. If we put the negative in here, we get 1/4 times rad 3 minus 1. All right, so it actually doesn't matter how you or which method you prefer, but personally I prefer using the triangle, right? Because I don't have to worry about the bounds. I just convert everything to trig function, work it out, and then reverse back to using x. Right? So this is our first example. I know it's still a little confusing, but let's try another one, and hopefully it will make a little more sense. All right, example 2, we have this integral. Now, this question is pretty interesting. It's actually one of the final questions from Calc 2 class in spring 12. Okay, so let's take a look at this. First, we want to identify what type of trig sub we're looking at, right? So we have x plus 4, which is the x squared plus 2 squared case, x squared plus a squared. Let's look at that. Go back a little bit. Right? So x squared plus a squared, or a squared plus x squared. We're going to let x be equal to a tangent theta. Right? So let's write it down first. Right? So let x be equal to a tangent theta. And while we're at it, might as well draw out the triangle that we're looking at to help us out a little bit. Okay, so we have theta here, and the tangent is opposite over adjacent, right? So that will be x, that will be a, and the hypotenuse will be square root of a squared plus x squared, or x squared plus a squared. They're the same thing. All right, and let's move on. All right, so dx, it will be a secant squared theta. Okay. Now, for this, I'm going to be using the triangle method instead of changing the bounds. So let's try to rewrite this thing. All right, so that's equal to 0 to 1. dx is a secant squared theta. And what is x squared plus 4 to the power of 3 over 2? So that is actually the square root of x squared plus 4 to the third power. So what we really want to worry about is what's the square root of x plus 4. Right? And again, you can do it fairly quickly. Right? So x squared plus 4. We know that we chose x to be a tangent theta, so that will be 2 tangent theta quantity square plus 4, right? Which will be 4 tangent square plus 4, and factor out the 4, you get tangent square theta plus 1, and tangent square plus 1 is secant square, so evaluate everything within the radical, you get 2 secant theta, right? So we have to take all these and to the third power, right? So we have 0 to 1. Oh, that's not a, that should be 2. My bad. All right, so that's a 2. That's a 2. Right, a is 2 in this case. So 2 secant square theta over that's 2 secant theta to the third power. I forgot the d theta here. All right, let's move it to the right. So 0 to 1, I now have 2 secant square theta over 8 secant to the third theta d theta. Right, so I can lose 2 powers of 2 of secant, and that's 4. So I'm looking at 1/4 and 1 over secant. That's just cosine theta. And after we integrate it, we get 1/4 sine theta, where x goes from 0 to 1, right? But we want to convert that back into x before we can evaluate 0 to 1, right? So sine theta, sine is opposite over hypotenuse. That's where we go back to the triangle, right? Right here, go back to here and try to find out what sine is, right? So sine is opposite x over hypotenuse, which is x over the square root of 4 plus x squared. And now we can evaluate it from 0 to 1, which is 1/4, 1 over square root of 4 plus 1 minus 0, right? Which is 1 over 4 times 1 over rad 5, which is, if you rationalize the denominator, you get rad 5 over 20. Right? Or if you don't want to rationalize it, you can write it as 1 over 4 rad 5. Right? They're the same thing. Not gonna worry too much about it. All right, so hopefully this example was a little more clear, right? So for any of the trig sub part, what we want to do is first identify which trig sub that you have to use, right? Whether it's x equal to a sine, or x equal to a tangent, or x equal to a secant, right? Once you pick that right one, you just follow the same thing, right? Build a triangle, rewrite everything in terms of theta, integrate it, and then go back to x by using the triangle. Okay, and then evaluate it at the same limit. All right, so let's do another one. Right, this one is going to be a little different. Let's take a look. All right, so here's another example that requires trig sub. Now, if you just look at this integral right here, 5 over radical 25 x squared minus 9, it's not exactly in the form of x squared minus a, right? So what we're going to do is we're going to factor out the 25 in the radical, right? And then bring out the outside, which gives me a 5. So I have x squared minus 9 over 25. Right now, in this case, we can see that we can write this as x squared minus 3 over 5 quantity square, right? In this case, our a is 3 over 5. And this is in the form of x squared minus a. So let's see which trig sub we have to use. All right? So x squared minus a, we have let x be a secant theta. All right, so here we're going to let x be equal to a, 3/5, secant theta. And let's also draw out the triangle as well. It will look like this, right? So hypotenuse is x and adjacent is a. Let's do that. Oops. All right, so hypotenuse is x, adjacent is a, so the other leg will be x squared minus a squared. All right, and then, oops, let me fill in the a, so a will be 3 over 5, and then that will be x squared minus 9 over 25. All right, so let's see what we have. Dx is equal to 3 over 5 secant tangent d theta, right? So let's rewrite our integral here. So the 5 is actually gone, right? 1 dx. All right, so integral of dx is now 3 over 5 secant tangent, tangent d theta, and then all over this square root of x squared minus 9 over 25. Right? So we can go back and look what we have. All right, so if x is secant square, then here x squared minus a squared is either a tangent theta or a negative a tangent theta. Right now, since here a is positive, right, we're gonna use this positive a tangent theta. All right, so which is 3/5 tangent theta. All right, and then we're gonna see a lot of things are going to cross out. For example, the 3/5, the tangent, leaving us just integral of secant d theta. Now, this is actually one of the tricky integral. It takes some time to show, and it actually has a bit of technique in order to integrate this. But if you look at integration table, integral of secant theta is ln of absolute value of secant theta plus tangent theta plus c. Okay, now all we need to do is replace the secant theta and tangent theta back into x using our triangle up here. All right, so let's see. ln of secant is hypotenuse over adjacent, right? Which will be 5x over 3 plus tangent is opposite over adjacent, right? So this whole thing divided by 3/5. So that's 5 radical x squared minus 9 over 25 all over 3 plus c. Okay, all right, so that's it. That's so a lot of the technique here I'm using is using the triangle method, right? And the way we got this is that secant theta is hypotenuse over adjacent. Okay, so sometimes you have to factor out the coefficient in front of x squared in order to get something that works like a trig sub. Right? And of course, not every question will require a trig sub. right? But before showing you guys that, I have one more that I'd like to show you. All right, so here we have an integral, and notice that inside the radical, it doesn't look like any of the trig sub. So one technique is we can complete the square before applying trig sub, right? Dx, right? And then we have to add a 4, and subtract a 4. So it'll look like this: 4 plus 4x minus x squared, and then minus 4. That. And then what I'm going to do is I'm going to look at these 3 terms and then factor a negative sign. All right, so I have dx square root 4 minus x squared minus 4x plus 4. All right, so that is a perfect square trinomial, which gives me dx square root of 4 minus x minus 2 quantity squared. Now, this still doesn't look like a trig sub, right? Because we, instead of x minus 2, we want just x squared here. All right, so here we're going to perform u sub, right? So u sub, let u be x minus 2, and du will be dx. All right, and then going dx, going again. All right, now we're not gonna worry about the bounds yet. So later on, we're gonna come all the way back to x. All right, so let's see. Dx is now du, and then in the integral, I have 4 minus u squared. Right now, that looks like a u sub, right? So in this case, we're going to let u be equal to 2 sine theta, right? And du is 2 cosine theta d theta, right? This is the first type of trig sub. All right, then now we have 2 cosine theta d theta, and the denominator, square root of 4 minus 4 minus u squared, will be 2 cosine theta. Okay. All right, and then you're going to see that everything actually crosses out, leaving you just d theta. Right? And then when we integrate that, we just get theta, but we have to go back to the original, right? So let's see. We know that u is 2 sine theta. That means sine theta is u over 2. So theta is arc sine of u over 2. Okay, so theta is arc sine of u over 2. Well, we're not done yet. We have to go back to x, right? So u is equal to x minus 2. All right, so go to the top here. We get arc sine of x minus 2 over 2. And now we're back into x, so we can put our original bounds in it from 1 to 2, evaluate it from 1 to 2. So we have arc sine of negative 1/2 minus, negative 1/2, 2 minus, so that's 0, arc sine of 0, minus arc sine of negative 1/2. Okay, so arc sine of 0 is just 0, minus arc sine of negative 1/2, that's the negative 1, that's negative pi over 6, right? Which gives me a positive pi over 6. Now remember that arc sine only takes care of the right-hand side of the unit circle, right? So it's going from negative pi over 2 to pi over 2, right? So that's the range of arc sine, negative pi over 2 to pi over 2, right? So when we have negative 1/2, we're looking at this angle right here, which is negative pi over 6. That's how we get this. Okay, and then yeah, that's the final answer, pi over 6. Now for this one, you can also do limit switching as you're moving along, right? For example, you can switch the bounds 1 to 2 and replace it with u, so plugging 1 and 2 in here to get a new bounds for u. And then when you're doing trig sub, also replace that and then put it in here, and you'll get the same answer, pi over 6. Right? The limit switching method, right? Which will also work in this case. But usually I like to stick to one method, master one method first before moving on to the other. So I don't know if you notice, but if you look at this thing right here, this integral that we have on the bottom, that's actually just a, if you just integrate that, you get arc sine, right? Arc sine of x minus 2 over 2, right? Which will make your life much easier, right? If you notice that this is arc sine, right? So, not everything that looks like this requires a trig sub. So it's either trig, but most of the time it has something to do with trig functions or inverse trig function in this case. All right, and that'll be it for today. All right, so let me go back and talk a little bit about this. All right, so 8.3, everything revolves around this table, right? Understanding this and how to use that during evaluating an integral is very crucial, right? So it might take you some practice, but also we will do some group work during our weekly meeting. All right, and that'll be all. Thank you guys. Have a good day.